Semiconductors and devices. Question arises, what is semiconductor? So, by free electron theory, on the basis of free electrons available in conductor, free electrons are very large in number. In insulator is very less. In semiconductor, in between. These free electrons are in between the two. But on the basis of band theory, can better differentiate between them. So, band theory, there are two bands, conduction band and valency band. In conduction band, if electrons available, they conduct. Here, in valency band, electrons are available, but they are not conducting. Here, in conduction, in conductor, valency band and the conduction band, they are overlapped. At room temperature, most of the electrons available in conduction band. Current is flowing even by very less potential difference. In insulator, conduction band and the valency band, they are separated by the energy gap. It is more than 3 electron volt. So, availability of electrons in conduction band is very less. So, we are not getting the current. If the energy gap is more than 7 electron volt, then almost no current, almost no electrons and no current flowing in insulators, even at very high voltage. Example here is porcelain insulator. Insulator using in high voltage transmission line. Semiconductor, the band gap between the conduction band and the valency band is less than 3 electron volt. Are called semiconductors. This energy gap is 1.1 electron volt for silicon, 0.72 volts for germanium, 5.6 electron volt for carbon, and almost 0 for tin. So, these are semiconductors. Here, compound semiconductors. First one is a gallium arsenide, GaAs, energy gap 1.43 electron volt, used for LED, red color or infrared. Gallium nitride, energy gap 3.4 electron volt, blue color LED. Gallium phosphide, energy gap 2.25, green color LED. And cadmium telluride, energy gap 1.45, red and infrared for solar cells. So, we are deriving the expression for the conductivity and the resistivity for semiconductor. In semiconductors, electrons and holes both are there. So, by the application of this electrical field given by voltage divided by the length of the conductor is the area of cross section of this semiconductor. Electrons are moving in the opposite direction of electrical field and holes are moving in the direction of electrical field. Due to electron and holes, both are the currents are moving in the same direction. So total current is given as I is equal to IE plus IH. Now what is the NE? Is the electron concentration, electron density or number of free electrons per unit volume. NH is hole concentration. VE is the drift velocity for electron. VH is the drift velocity for holes. Mu E is the mobility of electron and mu H is the mobility of holes. We know drift velocity is given by mu into E, where this is the drift velocity, mu is the mobility, E is the electrical field. Now, total current is IE plus IH. We know the formula of I is equal to NAEVD. So, here putting the values of IE, here N is the concentration, is the area of cross section, is the electronic charge, and V is the drift velocity for electrons. Similarly for holes, and VH is the drift velocity for holes. NH is the hole concentration. We are taking A and E common. Here NE VE plus NH VH. Here I equal to A E. We are putting the value of V, drift velocity, mu E. Mu is mobility, is the field. So, NE mu E plus NH taken out. I upon A called current density J is called current density. Here E Ne mu E plus NH mu H E. Equation 1. Now we know current density equal to sigma E. From equation 1 and 2, we get sigma conductivity is equal to E Ne mu E plus NH mu H. Equation 3. This is the expression of conductivity. Now, reciprocal of this is resistivity. Rho, reciprocal of this conductivity, so 1 upon E Ne mu E plus NH. As we know, though, conductivity of pure semiconductor or intrinsic semiconductor is very less. To improve its conductivity, we add some impurity, suitable impurity, either by 15th group or by 13th group. It is pentavalent, it is the trivalent. Pentavalent impurity or it is trivalent impurity. Deliberately, to the pure intrinsic semiconductor, this process is called doping. Impurity atoms are called dopant. From 15th group pentavalent, from 13th group trivalent, in the ratio of 1 10^6 or 8 or 10. 1 ppm means 1 particle per million, 1 particle of impurity atom to the pure semiconductor or silicon or germanium. It is sufficient to increase the conductivity as one dopant create one electron or one hole. Electron from the pentavalent, one hole from the trivalent. Here 10^22 dopants means number of electrons or number of holes created here 10^22 by the dopants. So conductivity increases drastically. Now let's say when we add impurity from 15th group pentavalent impurity atom, or sometimes it is called donor atom, here or just to learn BAAP, bismuth, antimony, arsenic or phosphorus, any dopant can be added to the pentavalence is pure semiconductor. In the ratio 1 is 10^22 means itne free electrons ho jayenge. Here the crystal of silicon, if we add the arsenic pentavalent, here 4 electrons are consumed to complete the octet. 1 electron is free. 1 electron is free, and here 10^22 number of free electrons per meter cube. So these are the number of free electrons available here. So conductivity increases drastically. Here electron concentration means number of free electron per unit volume is much more than the whole concentration. So we are getting the current because of the free electrons, negative type. So it is called N-type semiconductor, negative charge. An electron is called a majority carrier here. Now band diagram of N-type semiconductor. The gap between the valency band and the conduction band is 1.1 electron volt for silicon, 0.72 for germanium. And the donor energy level or donor energy state is just set below the conduction band at a gap of only 0.01 electron volt. अगर हम इलेक्ट्रॉन वैलेंसी बैंड से कंडक्शन बैंड के लिए ले जाएं 1.1 electron volt energy is required, but here only 0.01 electron volt is needed for the availability of conduction band in the electrons in conduction band. So we are getting the current easily at a gap of only 0.01 electron volt. Now suppose if we add the impurity from the 13th group called acceptor atom, here aluminum, boron or indium, Lb. Again one acceptor atom here creating the one hole because 3 electrons available, trivalent impurity atom. It is a trivalent impurity atom. So here 3 electrons are consumed to make the covalent bond, but 1 electron is required here, that is needed. So it creates a cavity hole. Hole means 1 electron is required here to complete the octet. So hole is creating. It is called deficiency of electron. Its hole positive charge. Here number of holes are much more than number of electrons free. So majority carrier is hole. current we are getting because of the doped holes and positive charge. So doped semiconductor from 13 group or by acceptor atom or trivalent impurity atom, it is called p-type semiconductor. Here band diagram, conduction band and the valency band are separated here 1.1 electron volt for silicon, but acceptor energy level is set just above the valency band. So electrons are jumping to conduction band, 1.1 electron volt energy required, but here acceptor energy, this is the holes, so electron is required here. When it is jumping from valency band to acceptor energy level, holes are created in the valency band, and this is responsible for the current. So it is called p-type semiconductor, and this is the band diagram. It means either you add the donor atom or acceptor atom, pentavalent, trivalent. In both the cases, conductivity increases drastically. Here we know Ne NH is equal to Ni square. Ne is electron concentration, NH is hole concentration, Ni is intrinsic or pure concentration. In N-type, number of electrons, 3 electron per unit volume, or Ne is electron density, hole density. Electron is majority carrier, in p-type, hole is majority carrier. N-type or p-type semiconductors are electrically neutral as a whole. Reason is pure semiconductor which is neutral, plus we are adding the impurity either by pentavalent or by trivalent. Both are neutral, so neutral plus neutral is doped semiconductor, or extrinsic semiconductor are also neutral. Formation of PN junction diode. Here P and N types of semiconductor are joined face to face. Here hole concentration is more, in N-type electron concentration is more. Majority carrier electron in N-type, majority carrier holes in P-type. Due to the attraction force, holes and electron they are coming closer, and in the depletion region they are depleted, means neutralized. P-type, N-type individually they are neutral, but one electron from N side is coming here in the depletion region, and hole from P side coming here in the depletion region, and they depleted, leaving behind here towards N side positive ions, and towards P side that is negative ions. And these positive and negative ions are immobile carriers. Positive and negative ions are immobile carriers, so they can't move, creating an electrical field, barrier electrical field, and barrier voltage. Barrier voltage is only 0.7 volt for silicon and 0.3 for germanium. But electrical field is very high. The reason behind here is the depletion, which is very small, of the order of micron level. So we are getting this electrical field here after calculation 7 into 10 to the 5 volt per meter. It is quite high. Now these holes are moving towards N side, but a force acting on holes due to the strong electrical field, barrier electrical field towards left, and force on electron due to the strong barrier electrical field is towards right, means this barrier field opposing the further depletion of holes and electrons. If electrical field barrier is not sufficiently large, it is able to stop the holes and electron depletion completely. Here one current, that is called diffusion current, because they are diffusing holes and electrons from P region towards the N region. So this is called diffusion current. Direction here is from P region to N region. It is due to majority carriers. Now from N side to P side, from N side P side, new current drift. Because of the high electrical field, they are drifted. This is the minority carrier. Because in minority carrier, N side is holes and P side is electrons. Now holes are moving because of this electrical field in this direction, opposite to N side to P side. It is called drift current. Drift current is from N type to P type, and diffusion from P type to N type. diffusion current is because of the majority carrier and drift current because of the minority carriers. At equilibrium, diffusion current and the drift current, they are equal and opposite. This is the formation of PN junction diode. Now let us say band diagram of PN junction diode. Here and side is positive, side is negative. Means band diagram of PN junction diode. Diode here is, let us say, P side, N side, and this is the T gap. The gap here depletion width very small, but here positive charge and negative. So voltage positive here, negative here, like this positive negative, and the gap here is 0.7 volt for silicon, and this is a 0.3 for germanium. This is the band diagram of p-n junction diode. When in forward biasing, applied voltage positive terminal is connected to P region, negative terminal is connected to N region. It is called forward bias. When in forward bias, if applied voltage is less than barrier voltage, then almost no current or very less current, no current flowing. VB sometimes called barrier voltage or knee voltage or critical voltage. If V applied voltage more than the barrier voltage or knee voltage, sometimes it is called knee voltage or critical voltage, then forward biasing current increases rapidly. And if applied voltage is very large, then after saturation, current is not increasing much. So this is the knee voltage. We are drawing the graph here for the applied voltage positive, and this is the forward bias current in milliampere, like this, almost zero. This is called knee voltage or barrier voltage, that is 0.7 for silicon. Current increases sharply. And after say 1.1 or 1.2 volt, saturation comes here. Means current is not increasing much. Means up to this point, it is called cutoff region, where we are not getting much current, forward biasing. And this is called active region, where current shoots up, current increasing sharply. After that, this is called saturation level, saturation region. Current is not much increasing. Even if voltage increases, current not increasing. Here in reverse biasing, negative is connected to P region and positive terminal is connected to N region. So there's no question arises of forward biasing current like in due to the majority carrier. But now for minority carrier in N region, that is the holes, in N region, that is the electron, this biasing or the voltage connected here is supports for minority carrier, opposing for majority carrier, supporting for minority carrier. So here applied voltage and the barrier voltage, they are added up. Effective voltage in biasing, reverse biasing, is V plus VB. They are supporting. In the forward biasing, they are opposing. The effective voltage here is applied voltage minus barrier voltage. Here there's V plus VB. So in reverse biasing, we are not getting current, almost zero current. That is because of the minority carrier, so current is very less. But a stage comes that is called breakdown voltage. Breakdown voltage. After the breakdown voltage, current is increasing sharply. Here maybe depends on the doping level. So roughly 9 or 10 volt, 8 volt, somewhere 5 to 10 volts roughly. This is breakdown voltage. After breakdown voltage, current reverse biasing increasing, but it is much less than the forward biasing, because forward biasing current in milliampere and reverse biasing current is in microampere. Now, what is the breakdown voltage? Sometimes it is called avalanche breakdown. Characteristics for reverse biasing. In reverse biasing, negative terminal of the battery is connected to P region and positive terminal is connected to N region. For majority carriers of P region and N region, this reverse biasing opposes. So, no question arises of current due to majority carriers. But for minority carrier, it is supporting. Reverse biasing, positive terminal is coming here and holes are reverse minority carrier, so it is repelling, and electrons are repelled by the negative plate. So they are crossing the junction, and positive negative means here the effective voltage in reverse biasing is applied voltage plus barrier voltage. Reverse biasing minority carriers are very less, but if we increase the applied voltage, V plus VB is so large in covalent bonds break at or above which, that is called a breakdown voltage. When covalent bonds break, suddenly increment in the minority carrier and current in the reverse bias increases suddenly after breakdown voltage. In reverse biasing, in forward biasing, resistance in forward biasing, that is very less, roughly 50 to 100 ohms. Ideally, forward biasing resistance is 0 and depletion with decreases in forward biasing. In reverse biasing, resistance is very large, of the order of mega ohms, ideally infinite, and depletion with increases. In half wave rectifier, only half wave is in DC. Means only half wave is rectified. AC to DC half wave or positive half cycle. Here at P plus 4 volt, at N it is at 0 volt. So diode D is at forward biasing. In forward biasing, less resistance operates, conducts. So this cycle, positive half wave cycle, is converting into or going into across load resistance. It is appearing across load resistance. For negative half cycle at P region, minus 4 volt, at N region 0 volts. So diode is reverse biasing, posing very high resistance, so it will not conduct. No output we are getting. For positive half cycle, it conducts, appearing across load resistance across say XY, and for negative half cycle we are not getting any output. So this way half cycle is the output, rectified only half wave, called half wave rectifier. Here full wave rectifier, here full wave rectified is here for the input and output of transformer is 180-degree out of phase. For positive half cycle or positive half cycle, P1 at plus 2 volt and center tap at 0 volts, at N1 and N2 0 volts. So diode D1 is at forward bias, it conducts. So positive half cycle appears across load resistance RL, but flat at P2 minus 2 volts and N2 at 0 volts. So diode D2 is at reverse biasing, it will not conduct. Or negative half cycle at P1 minus 2 volt, at N1 0 volts was a central tap. So diode D1 is at reverse bias, it will not conduct, and at P2 plus 2 volt and at N2 0 volts. So diode D2 is at forward bias, it will conduct. So this negative half cycle appears across RL as positive half cycle. Why? See, in first case, the direction of current is like this, is the current here flowing like this. So X to Y, direction of current from X to Y. In this case, current is flowing like this, and this is like this. So here also current is flowing through the load resistance the same direction. That's why it is DC, not AC. So for full wave rectifier, full wave is rectified into DC, converting into DC. For positive half cycle, D1 is operating, we are getting the output. For D2 also we are getting the output, but direction of current is same, not changing at all. So DC, not AC. This way we are getting here DC output, full wave rectified. Say for diode D2 is at forward biasing, it will conduct. So negative half cycle appears across the load resistance as positive half cycle. Why? See, in first case, the direction of current is flowing through D1 diode like this, and through the load resistance direction of current from X to Y like this. But in second case, for negative half cycle, here direct diode D2 is working, conducting, direction of current is like this, to the load resistance again X to Y like this. So in both the cases, for positive half cycle as well as for negative half cycle, we are getting the current as positive. So this is the input and this is the output. Full wave is rectified. Ripple factor is given as I RMS value 1I DC part square minus 1. It is 1.21 for half wave is quite high, means AC part is much more, but for 0.48 for full wave rectifier, half wave rectifier. Here efficiency is 40.6% only in half wave, and form factor means the RMS upon DC 1.457. Hello. Ripple factor in DC is defined as IRMS upon IDC square minus 1 whole root. The ripple factor for RMS half wave rectifier is 1.21. Efficiency for half wave is 40.6%. Form factor VRMS upon VDC 1.57. VDC part V maximum upon pi, IDC I maximum. Whereas for full wave rectifier, ripple factor is low 0.48, IDC part 2 I maximum upon pi, VDC part is double V maximum pi into 2. Efficiency is far better than half wave 81.2 double. Form factor is also good 1.1, lesser than form factor in half wave. So by comparison also we can say full wave is better than half wave. In filter circuit, AC part and DC part are separated or filtered. Say this is the repelled or pulsating input DC. This is RC filter. This XC will be capacitive reactance 1 upon omega C, 1 upon 2 pi nu C. Nu is the frequency. For DC part frequency 0, XC will become infinite. It will behave like open circuit. So DC part will not flow through the capacitance but coming across the output RL resistance. Now for AC part, frequency is quite high. XC reactance, capacitive reactance will be low. So this current flow because of less resistance, and to the high resistance in the series circuit will become convert into heat and finished. So for half wave, if input is 50 cycle per second, frequency of half wave rectifier is 50 Hz, the same, but in full wave rectifier it will become double. एक साइकिल का डबल हो गया, 2 साइकिल हो गई. So learn it. In half wave rectifier frequency remains the same. In full wave it will be double. Hello, we are discussing photodiode. Photodiode, PN junction diode made from the photosensitive semiconductor and provide a transparent window to allow light fall on its junction. This is the symbol of photodiode. Here photons are falling on this junction, PN junction, having this energy H nu must be more than the energy gap. It is always reverse bias. When photon energy is greater than the energy gap, it generates photo charge carriers near the depletion region. Here, due to the junction field in reverse biasing like this, what will happen is electrons moving towards N side and holes moving towards P side because of this barrier field, and this applied voltage, applied field is supporting here. So this is increasing. Due to this fact, electrons are moving towards this side and holes moving towards this side. Means here, if electrons are collected towards N side, holes towards P side, it creates EMF and current through the load resistance R like this. So change in photo current, this is the photo current here. Change in photo current depends on the intensity of photons falling on the junction. If intensity is more and more, it means current is more and more. Number of photons more, number of electrons, and current increasing. So this is the graph between the voltage and the current in reverse biasing. If intensity increases, I3 is more than I2, more than I1. If intensity increasing, reverse biasing current is also increasing. Here necessary condition here is energy of the photon must be greater than the energy gap. By increasing the intensity, current in reverse biasing also increases. Here some usage of these photodiodes in detection of optical signals, light operated switch, it can be used as electronic counter. In elevator and lift also can be used. Hello, it is a light emitting diode LED. Hello, it is the light emitting diode. Thought it is LED. It is the heavily doped forward biasing PN junction diode, which instantly converts the biasing electrical energy into the optical energy. It gives normally infrared and visible light. Infrared signals are used to operate TV like remote sensing, remote control, and visible light LED are used in many places. We'll discuss. So this is the symbol of LED, or this, it is the forward biasing. This signal is forward biasing because positive terminal is connected to P region and negative terminal is connected to N region through the resistance. A PN junction diode made from the semiconductor like gallium arsenide or indium phosphide with metallic contacts like this P region, and this is for N region. Here this is a transparent sheet through which photons are coming out in the form of light or infrared signals. It is the forward biasing through series resistance R. Photons are emitted from the non-metallic surface in N region. The series resistance R limits the current because if R is less, current will be more. If R is more, current will be less. So it can be used to limit the current in the circuit. And current in the LED, it can be controlled. Intensity also, if current is decreasing, intensity decreasing, and vice versa. When the PN junction is in forward biasing, holes move from P region to N region and electron moves from N region to P region. Means here the minority carrier in N region and P region, minority carriers increases. On combination, energy is released in the minority carriers in the form of photons. If the photon energy comes in infrared region, means it can control things like TV, remote control, or if colorful light is coming out, we can see the different colors of LED. Here, if voltage increases, forward biasing current increases, we are getting here infrared signals, red color, yellow color, green color, blue color, here white color also. Like, it depends on how much current is and at what voltage. Say, important features of this LED, colors of light emitted by LED depends on the band gap energy. If the band gap energy is something due to which the wavelength may be coming in for red, yellow, and different colors. So LED is giving you different color light depending upon the band gap energy. So which type of LED we are using for different colors? For the same region here, energy gap. And energy gap is different for different colors. So second point, intensity of light emitted determined by the forward current and the energy gap and the wavelength or frequency of the photons coming out. Here, energy gap minimum 1.8 electron volt must for visible spectrum. If we are using say gallium arsenide phosphide, where energy gap is 1.9 electron volt, is used for red color LED. Gallium arsenide energy gap is 1.4, it is used for infrared LED. So what is the color coming out from the LED? It depends on the which semiconductor we are using and what is the energy gap for this. Now, so LED can be used in optical communication, image scanning, and indication lamps, digital clocks, mobile, calculator, music system, different color displaying here, and railway station, airport, etc. Hello. Solar cell. Here we know what is solar cell. Solar cell is, say we are converting the sun energy, solar energy into electricity. Here we are using PN junction diode from silicon or gallium arsenide. Here P region and very thin layer of N region. Why thin layer? Because the sunlight coming from this photons or sunlight having some energy. If it is coming to the junction, it is only possible when this N region is very thin, and these are the electrodes, and here this is the metal cap through which we can connect it. Say it is, say, like this P region, N region, and this is the depletion width. If the photons or sunlight is coming falling on this junction and the energy is more than the energy gap, then what will happen? And solar cell emitted light or photons energy is more than h nu h by lambda is more than the energy gap. It generates EMF, and electron and holes pair due to the excitation of electrons from the valence band to the conduction band, and light energy is this near the junction. What will happen here? Electron moves to N side and holes move from towards the P side. Because of this, the voltage difference across the PN junction. P side holes more and more, N side electrons more and more, and across this sufficient voltage generated. So because of this voltage difference, a current flows to the load resistance. Here. Now, current is proportional to the intensity. It means if intensity of sunlight is more and more current flows here in the circuit. So sunlight is converted into electricity. This voltage is called, say, open circuit voltage, and this is called short circuit current. So this is the maximum current flows here. Semiconductor made from the silicon, their energy gap is 1.1 electron volt, and gallium arsenide, where energy gap is 1.43 electron volt, and cadmium telluride, energy gap is 1.45 electron volt. There are the usage of solar cell for charge storage battery daytime, and we can use it in night or whenever light is not available, electricity is not available. We can use of battery by the inverter from DC to AC, convert and use the electricity. It can be used in wristwatches and calculators, in spacecraft also, in solar panel also. These are the usage of solar cells.